Welcome everybody. Welcome to one more telecom seminar, which is hosted by Technology Innovation Institute. For today, it's a great pleasure for us to have Professor Kaibin Huang from the University of Hong Kong. Professor Kaibin Huang received the bachelor and the master degrees from the National University of Singapore and the PhD degree from the University of Texas at Austin, all in electrical engineering. He is a professor and associate head at the Department of Electrical and Electronic Engineering at the University of Hong Kong. He received the main awards, especially he received the AAA Communication Society 2021 Best Survey Paper, 2019 Best Tutorial Paper, 2019 Asia Pacific Outstanding Paper, 2015 Asia Pacific Best Paper Award, and the Best Paper Award at AAA Globecon and AAA ICCC 2018. He received the Outstanding Teaching Award from Yonsei University in South Korea in 2011. He has been a highly cited researcher by the Clarivate Analytics in 2019 to 2021, and he was awarded a research fellowship by Hong Kong Research Grants Council. And he has also served as the chair of many symposiums, which includes IEEE Globecon 2017 and 2014. And he is currently executive editor of IEEE Transaction Wireless Communications and editor of IEEE Journal Select Areas and Communications, and other editor of IEEE Transaction Communications in Network. He's also a distinguished lecturer of IEEE Communication Society, Vehicle Technology Society, and he's a AAA fellow. Well, in his talk today, he will discuss a very hot research area, which is called edge intelligence. And to understand more this paradigm that exists in communications, this paradigm shift, three questions will be asked. The first is reliable communication always needed? The second is interference always a foe? And the third is analog computing outdated. So he will introduce some 6G edge intelligence technology that feature the communication computing fusion. So Professor Kaibin Huang, thank you so much for your time and for accepting our invitation. So without further ado, the floor is yours.
Thank you, Daniel, for the invitation and kind introductions. So today I want to talk about edge intelligence and a common question is what is new here? And so I basically want to introduce some ideas about how it has changed the paradigm of communication and also computing. So the background is 6G. 6G so it's under lots of research right now, including at TII, I'm sure. So in 5G, life is simpler. 5G, we just look at wireless communication here. 5G communication, why? Actually, mobile networks are very complicated, has a lot of operations like sensing, control, computing, communication. But just that 5G decouple all these functions and do them separately. So 5G is simpler, I would say. 6G is too ambitious. 6G want to achieve a lot. And this decouple approach is not a separation approach, it's not sufficient, right? So 6G researchers are pursuing an integrated approach, integrating communication, sensing, computing, control. And today I want to talk about two aspects, communication and computing. How are they being integrated? So then talk about computing. Computing is also undergoing a revolution. 10 or 15 years ago, everybody talked about cloud computing. But in the past decade, the gravity of the computing is shifting from the cloud towards the network edge, living on the edge. Why? There's three reasons for that. The first reasons, microprocessors are becoming very, very cheap. Every single device these days has a computer inside. So they generate data, they are smart. And data has become the world's most valuable resource. Why? You look at the most valuable companies in the world. Amazon, Google, Facebook, maybe not Facebook, this day is not doing so well, Microsoft, and so on, right? All these companies are data companies, the most valuable companies in the world. They have exceeded fuel or finance to become the most valuable companies. So their second strength. The third strength is the exponential growth, not just smartphones, but in general edge devices, including sensors and all the connected devices, IoT devices. The total population is going through an exponential growth towards tens of billions of connected edge devices. All these devices with a computer is 24/7 generating a huge amount of data. As we say, data is the most valuable resource. You know, there's some number here. About 150 trillion gigabytes of data is waiting to be analyzed by 2025. Why these data are available? One aspect is that you can collect this data, use machine learning algorithm, and distill from the data artificial intelligence, which is very useful. It can empower our next generation applications. In 6G, this is especially important. The ubiquitous availability of AI is especially important to realize the 6G vision of connected intelligence. 6G connected intelligence, what do you mean? We used to connect people, human beings. What do you mean by connected intelligence? Intelligence is not just human being, because machine also has intelligence. Connected intelligence means connect human to be human in a better way, connect human to machine so that machine and human can interact with each other. And we also try to connect machine to machine. All of them have intelligence. So this communication scenario is very diversified, and therefore edge intelligence provides an engine, provides an infrastructure to build for this kind of diversified communications. 6G not just want to be intelligence, it wants to be faster even than human beings. One goal of 6G is to reduce the air latency to just 0.1 milliseconds. This is 10 times faster than human beings. Humans is just 1 milliseconds. This is Jackie Chan from Hong Kong, the place I'm in right now. That's a 1 millisecond, and the network wants to be 10 times faster. Why? So that the network, the AI in the network, or called network AI, can be used to empower a wide range of applications, especially virtual reality, augmented reality, to make them smart. AI can be used to provide services such as biometric recognition, intention perception, and so on, right? For VR AI applications, the required tactile delay is 15 milliseconds and visual delay is 15 milliseconds. Now, you have to take note that this delay comprises everything, end-to-end delay. It comprises communication, computing, network protocol, and so on, right? So we need to make sure the air latency, the communication latency is far below the requirement, so that when you combine everything together, it works. So that is the background here. If you want to achieve all these ambitious goals, traditional communication is not enough. Let's just call Shannon 1.0 traditional communication. Why? Because it's based on separation approach. So Shannon 1.0 is basically based on rate maximization. Try to maximize the data rate so that we can build a very big pipe transporting data from one place to another place. If you be more precise, the objective is, given a constraint on distortion, you want to transmit as much data as possible. This is a brute force approach. It is not directly addressing the edge intelligence problem in the 6G. So we require an upgraded version. It's called Shannon 2.0. Its objective is not brute force rate maximization. It is fast edge intelligence. We can reframe the objective. Given a constraint on the learning and decision accuracy, we want to distill and use intelligence as fast as possible. You see, this is a very different objective, and therefore the paradigm of communication has shifted towards something new. I will tell you why. But for concrete discussion, we need to figure out that what are the use cases of edge intelligence. 3 use cases are being discussed in 3GPP. One is federated learning. So the bunch of data everywhere. Federated learning is trying to use all the data to train a global model, a global AI model, while protecting the privacy of all the data. Okay, so federated learning. So after the model are being trained, then you use the model to provide inference services to the devices. Typically, you don't want the devices to upload the raw data because it's private. So you use a split inference, the second use case. A single model, you cut one part and run it at the devices. The bulk of the model was kept at the server. The on-device model basically extract the intermediate features from the data to protect its privacy, and yet keeping the features useful for inference, and then upload the features to the server. The server will do most of the job. It will perform inference on the feature, recognize a pedestrian, recognize is a cat, is a dog, is what is the intention, and what is the face, and what is your anything, intelligent task. And then you download the inference result to the device. The device could be a robot, and could be the UAV, could be your mobile phone, and could be your goggles, right? So the third use case is called model downloading. You just download the whole model, which is a small or mid-sized model, onto a device. Why? Because these days high-end smartphones are all equipped with a very powerful AI accelerated hardware, such as GPU or some other hardware. So it's capable of running, executing an AI algorithms. So you in the network, you have an AI library. You store millions to billions of AI models targeting different applications and scenarios, just like your apps is an app library, but except that it's an AI library. So you just based on the request, you download the model onto the devices, real time and in demand. And so what is the advantage here compared with split inference? The response time is shorter, and it's better privacy and context location awareness, and so on, right? And so these are the 3 use cases are being considered for 5G and also 6G standards. Our discussion will relate to these few cases. So what is the problem here? In terms of communication, the problem is that all these use cases will involve a transmission of a high-dimensional model parameters or high-dimensional features or high-dimensional training data over the air a lot, because a lot of algorithms are iterative. And so it basically creates a communication bottleneck. So in 5G is already heavily loaded, you're going to add an edge intelligence, but there's some other services they are jamming the network, like machine type communication, mobile broadband, ultra reliable low latency communication, and all these different other services already make the network really heavily loaded. So this is going to be a problem if you add an edge intelligence, which is a data intensive services. And even for 5G, although the commercial advertisement always say 1 gigabit per second, no, in the real life, the user experience rate are much lower. It's something like a 50, 100. You can argue with me, maybe 200 or 300, but it's the same order of magnitudes, and it's not very fast. So essentially, when we look to the 6G, we need to solve the communication bottleneck problem. This is requires a new thinking, new philosophy, and therefore. That is the topic for today's talk. So, in 6Gs, you got to take an integration approach. You got to merge 2 areas to improve the system efficiency. In the context of edge intelligence, you will be integrating communication and AI. Okay, so this basically is a virtual meeting. Metaphorically speaking, 6G will be Shannon meeting Turing. Because Claudius Shannon, is the father of information theory, and Alan Turing is the father of AI. So basically, this is a virtual meeting between them, or is a fusion of their representative areas. this is not coincidental because these two towering figures were friends in their lifetime anyway. And Shannon is actually considered a father of AI, as evidenced by this 1956 Dartmouth conference. All these participants are founding fathers of AI, and one of them is actually Shannon. All right. So this fusion is not coincident, not a coincident, I would say. Okay. So what's new here? What's new here? So what's new here? As Daniel introduced 3 questions I want to ask. So I want to ask the first questions. Before that, let's look at these pictures here. Now, the right-hand side pictures is Martin Cooper. I think there's is some question. Let me see. Oh, sorry. I thought there's a question for me. So in the right-hand side is Martin Cooper. He is the inventor of the 1G phone. 1G phone is the analog phone based on analog technology. It based on frequency shift keying or amplitude modulation without coding, so the quality is not very good. As a father of digital age, you can imagine Shannon will give some comment like this: "Hey Martin, this is a digital age. Your unreliable old toys need a Shannon coding. It's outdated, right?" Well, so the question I want to ask is this: is analog communication dead? Is analog communication dead? Since all the devices, all the modern communications are based on digital communication, is analog communication dead? So I'm trying to rethink and trying to find some interesting new answers to these questions here. So let's review what's the problem with wireless communication. The fundamental problem of wireless communication in terms of radio access is the radio wave superposition. This is a typical communication channel where a lot of users try to access the channel. They want to get through the resource constraint channel so that get to the other side, reliably. And so basically, there's an influx of multiple data streams through a finite channels here. So because of radio wave superpositions, all the simultaneous links generates interlinker interference. So how do we deal with this problem? We just take the approach of cutting pizza. A lot of people tell me that you should be cutting cake. Cake is more common. Sorry, I don't like cake, so I'm going to just use pizza. So we basically take an approach of cutting pizza into different slices and give each user one slice. What is the problem here? The size of the pizza is finite. If you have a lot of users, everybody is just going to get a small slice. It's not enough for high-rate communications. So how do we change this philosophy, solve this problem, and without asking for more radio devices? So edge intelligence, you look at edge intelligence, or you look at 6G, a lot of network operations are performing distributed computing. It's not doing radio access. So distributed computing, a lot of users still want to transmit data over the same channel, but at the output, at the other end of the channel, you are asking for an aggregated function of the distributed data. You're not asking for all the data. You just want to have an aggregated function, like average or something like that. So by that, you can actually change your philosophy. Shift your philosophy that actually interference can be a friend. If you change that philosophy, new technology can be invented to solve this problem. One technologies we also help to develop is called analog over-the-air computing. It's based on uncoded linear analog modulations. So the idea is, these days over-the-air computing is applied a lot to federated learning, although not necessarily so. So let's just look at a federated learning system here. So federated learning, basically you ask the devices to train a model and generate local model using local data, right? And all these local models are not accurate. So the server are going to ask the devices to upload all the local models. And what the server is going to do is going to do model averaging, like this equation here, just doing averaging of WK. WK is the local model. The averaging suppresses the inaccuracy, assuming that inaccuracies can be modeled by noise. So averaging are doing suppressing the model noise here. So that's what really what the server wants. It does not want to know the local model. I just want to know the average. So what researchers, including us, propose is that why not each devices use uncoded linear analog modulation to modulate the local model and transmit it over the air simultaneously with all other users. Because of radio wave superpositions, what the server receives is exactly the average of the model. What is interesting here is this is simultaneous access scheme. You do not need to cut a pizza. You just use, everybody has the whole pizza and eat the pizzas. So there's no scalability problem. And by that, you can really accelerate the learning process. Now, I just show some numerical results here. This is a experiment for training a global model for recognizing an MNIST data set. And so the vertical axis is the communication latency for achieving certain target accuracy. The horizontal axis is the number of devices. Now, as the number of devices increases, the traditional orthogonal access, in this case is OFDMA, the latency is going to increase linearly. But if you use broadband over-the-air computing, in short, AirCom is constant, not affected by the number of devices. So that solves the communication bottleneck problems here. Okay, and the story is very simple, but actually AirCom or over-the-air computing has become an active area because there are a lot of challenges. I don't want to go through all the technical challenges. It's going to be technical and going to take more than the time I'm given. So let me just say that all the techniques for all the research on AirCom is the main focus is wave shaping. You try to shape the wave. This reminds of me a great sculptor that I really admire a lot. It's called Michelangelo. So Michelangelo, it reminds me of this wave shaping is an art, right? And so Michelangelo is focusing on sculptures. So he has a famous quote: "I saw the angel in the marble and carved until I set him free." That's very, very nice saying. So I just modify his quotes a little bit. Wireless engineer, when designing AirCom, we see a function in the air and we shape it until the air becomes a computer. That's a lot of similarity. Therefore, that's the similarity that is in my mind. So this is the wave shaping. Why do you want to do wave shaping? Because the transmitted signal are not just added in the air, but they're being distorted by individual channels. So we need to shape the wave to overcome the channel noise, the channel distortion, so that at the output, we can get what we want, a specific function, what we want. So the bunch of functions you can choose from. Some want average, some want a geometric mean, some want to select the maximums. It is an art, except that our tools is not the knife, but it's just a different techniques people have invented, like OFDM subchannel selection, retransmission, MIMO precoding. At the receiver will be aggregation beamforming, and then at the transmitter there will be power control. All this technique is a tool to shape the channel so that we can perform over-the-air computing in the air. So this is the true spirit of the AirCom, and that summarizes all the gist of the research on AirCom here. I go a little bit technical. Here I just want to show that, when you consider end-to-end performance, like in this case, AirCom, federated learning, and also wireless communication, sometimes a lot of interesting new insight can come out. For example, in this, I just pick an example from our work here. So basically, this example is about network densification. It's about a network performing federated learning, and this stochastic gradient, which is actually federated learning is based on the stochastic gradient descent algorithm. The gradient is being perturbed by intercell interference and degrades its performance. So when network becoming denser and denser, you are expecting the gradient, the quality of gradient to degrade and then affect the learning performance, right? There's a trade-off here. When you have more and more devices, network become denser and denser, you have more and more data to train the model, and the model becoming more and more accurate. So there's two opposite trends here for network densification, data and interference. Two opposite effects. The question to ask is that when we densify the network, what is the net effect? So you actually mathematically, you can use a stochastic geometry to figure out that the net effect is good. The net effect is good because the trick here is that federated learning over there computing, there's an averaging operation, right? The averaging operation can have interference or suppression. So so when you do densification, the interference will be suppressed by averaging, but you have more data to help the learning. So as you can see in this curve here, this is average learning accuracy overall of the whole network, and then the horizontal axis is device density. When you increase the device density, the learning accuracy, the learning latency actually decreases until you saturate, because the data is enough already. You cannot improve anymore. So I just want to show you end-to-end end-to-end design actually brings us a communication computing fusion aspect, and which brings us a lot of interesting new insight here. All right. Okay, so let's shift gear and talk about Shannon's theory again. As we go into 6G, Shannon's theory start to show is a limitation. So we know Shannon's theory is basically about error correction. We want to transmit a sequence of bits from one place to another place. When error happens, we can correct the error, and we ask our questions, what is the fastest rate we can transmit without any errors, right? Okay, so this is reliability guarantees. So essentially, Shannon's theory is focusing on reliability and rate-centric. His assumption is that all these devices has no intelligence at all. They are just a dumb devices. All right. So therefore, this is a basic assumptions. He has a contemporary, also a collaborator called Warren Weaver. Warren Weaver, in his paper, he made this comment here. Right? He said Shannon's theory just solved the technical problem, which is transporting data from one place to another place, right? But actually, communication is more sophisticated and has a higher level. The higher level would be semantic level that concerns of the meaning inside the information or the messages. Also concerns how effective a communication can execute a task. Now, these two aspects now becomes very popular in 6G communication, and we see the increasing attention paid to semantic communication, paid to task-oriented communication. All these originated from semantic and effectiveness level that Warren mentioned, that is above the technical problems Shannon trying to solve. Okay, so let me show you one examples here. Shannon assumes no intelligence for transceivers, right? Let's assume the transceiver now is an intelligent robot. His name is called Rob. So Shannon tried to transmit a message, something like this. Hey, Rob, do you know Einstein's son, blah, 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 is a blah, blah, blah at university, blah, blah, blah? There are a lot of errors here. This is not a reliable message at all. But the intelligent receiver, Rob, is able to decode the message. Sir, the channel is noisy, but I guess what you meant is Hans Albert Einstein was a professor of hydraulic engineering at the University of California, Berkeley. Perfect. All the errors corrected. Why? Because he has intelligence. He has access to a database. He is able to fill up the blank in the sentences. And therefore, it makes us think that, naturally, it makes us think about these questions. Is reliable communication always needed? That's a question, a 6G question. All right, so let's look at these pictures. I'll explain to you why we need to look at this picture here. This picture is at the border of North Korea and South Korea. Have you guys been to the border of between these two countries? I've been there before because I used to live in South Korea. So this part is the most dangerous part of the border. It's called military demarcation line. So the soldiers of North Korea and soldiers from South Korea, they can get near this line as close as possible, but you cannot cross the line. If you cross the line, shooting will immediately start and the war will be triggered. Okay, so that's why I want to talk about this line here. Now this is in my mind is always similar to the boundary of a classifier. So if you look at the lab pictures here, this is the drawing is drawing the boundary of a two-class classifier, and the red stars are data samples from class 1. The blue stars are data samples from class 2. And these data samples for this classifier, you can get near the boundary as close as possible. But if you cross the boundary, an error will be triggered. Classification error is wrong, the result is wrong. So to understand the robustness of the classifier, there's a definition called margin. Classifier margin is measuring the nearest distance of a data sample towards the boundary. Right? So this margin characterizes how robust an AI model towards perturbation and noise. Right? So if you look at the right hand side, this figure here, we try to add noise to the data samples. So additive noise variance. When we increase the additive noise variance, the accuracy of the classifier is not affected at the beginning. It's not affected at the beginning. Only when the variance exceeds a certain threshold, the accuracy, bam, will suddenly jump and degrades significantly. So this the plateau. The flat part represents the robustness of a classifier. It means that even you try to perturb the data, the AI is able to absorb the impact without performance degradations. So I want to show you a more specific system here. This system is an AI-empowered distributed sensing. It basically comprises of multiple sensors. They try to observe an object from different angles, and then each extract out the features and transmit using aircom over the air. We discussed just now. Analog is exposed to channel noise, but it's highly very fast. And the receivers, here there's a function we designed. It can perform different aircom functions like averaging. That's called average pooling, or maximization. That's called max pooling. So we try to look at the mean square error of this aircom, the effect of mean square error. Now we run some simulation using some data set called a model net, and the accuracy, when you increase the MSE, the accuracy is not changing at the beginning, and also after sometimes it will drop, right, after the MSE exceeds a certain threshold. Now it shows a certain margin here, which is the tolerable noise here. So that means that if we, in the AI applications, if we are able to control the channel noise within the margin here, it's okay. We do not need to suppress the error to be 0, but just we need to regulate the error. So it seems to suggest to us is that reliable communication may not be always needed. But actually, we can even go one step further to argue that reliable the channel noise not just always hostile, it can be also beneficial. Why? Let's come back to the federated learning. And federated learning is based on stochastic gradient descent. And sometimes this gradient descent could have a problem. The problem is called the saddle point. So when you encounter a saddle point, the gradient is equal to 0, and you cannot continue your descent. So what computer scientists propose is that to add some artificial noise to the gradient so that it can escape from the saddle point, right? So what we propose is that, well, since it's a noise, we have abundance of noise from the channel. So why don't we use a channel noise to try to help the escape from the saddle point? So therefore, and in that, we can turn channel noise into an accelerator. But of course, this is not always true, because outside saddle point, for example, in the global optimal region or at a non-stationary region, you don't want so much noise. You just want to descend as accurate as possible, right? So you require some careful design of the power control algorithm, recognizing the characteristic of the descent region, and so that you can control it and adjust the effect of the channel noise. But if you do this kind of intelligent control, you are able to accelerate the gradient descent by using the channel noise. So channel noise could be also useful. So this discussion seems to suggest that for 6G, we can have a new kind of unreliable connectivities targeting edge intelligence. Now for 5G, the 3 main type of connectivity is enhanced mobile broadband, ultra reliable low latency communication, massive machine type communication. All these are reliable connectivities. What is the problem with reliable connectivities? Now, Shannon's theory says that this curve is from Shannon's theory. Error probability versus the coding length. If you want to achieve error probability, you need to increase the code length as long as possible, very long. Actually, Shannon's channel capacity is achieved when the code length goes to infinity. What is the problem of code length goes to infinity? Remember Jackie Chan? You remember 1 millisecond over the air latency? We cannot wait for so long. We want a very short packet so that we can act, faster than human beings, right? So if you allow certain unreliabilities, you can reduce the code length and have some error probability and use AI model to absorb the impact of this error probability. So by that, it has no problem. Okay, so, and it suggests that in 6G, with the widely use of AI, possibly there are some low latency, unreliable connectivities. So that's just some suggestion. I'm not very sure if industry is going to push for that, but it seems the messages seems to pointing to these directions. And so that is the answers my second questions I was asking just now. All right, so why don't we shift gear to talk about computing, since we have been talking about communications. So we can imagine, you look at the right-hand side picture, these are very interesting pictures. This picture, actually, in the picture is Alan Turing. And Alan Turing is using an analog computer to crack Nazi's Enigma code in World War II. This is an analog computer, obviously. We can imagine Shannon as a father of digital computing and communication. He probably makes some comment like, hey, Alan, even my phone can do a better job in cracking Enigma code. Means that our phones, our digital computer, much more powerful than this one here. So the last question I want to answer in this talk is that, is analog computing dead? Is analog computing dead? Except me, all of you, I'm sure you say yes. The answer is yes, it's computer. Why? I understand you, why you say so, because you can do a simple comparison. To be fair, so analog computer is just a specialized one-for-one problem, like the Enigma code cracking devices you saw on the previous slide. But digital computer is based on a transistor. It's based on Boolean algebra. It's very flexible, as you can see from your smartphone or your Apple computer. And analog computers has a small errors that can accumulate over time. So, but digital computer is resilient to noise. No error at all. And because of this, analog computer cannot reproduce the original result twice. But digital computer, you can always pull out the photo 10 years ago, still the same photo, look exactly the same. And more importantly, digital computers, because of the invention of solid-state electronics, it allows a very large scale integration and allowing us to make the computer chips very small and put into our small devices like sensors. So, and so that the answer seems to be obvious, especially you look at the powerfulness of the latest digital computer. You look at these chips are built by Cerebrus wafer size chip is huge. And it comprises of, this is state of the art for running the GPT-3 model that shows a human intelligence, comprises of hundreds of billions of parameters for its models here. Now this chip here comprises of 1.2 trillion transistors, 400,000 AI cores. How many cores do you have for your computer? Mine has just 8 or 16 at most, right? So this is a huge, it's amazing for digital computers. Okay, so what else do I want to talk about then? I want to talk about the limitation of digital computers. After all, no computer can be smarter than our brain. So people try to emulate our brain using by constructing digital brain. There are two ways of constructing a digital brain. The right hand side is we are very familiar. This is a neural network model. Neural network model essentially it's implemented using software, and the parameters, the weights of the the models are the parameter we can try to optimize. This is using machine learning algorithms. So this one we are familiar. Now the left hand side is called a neuromorphic computing chip. It's trying to emulate the communication between our neurons. So our neurons are the interface of two neurons is called synapse, and is a communication is using spiky signals, and it is the information is carried by the plasticity of the signals. For example, you can control the spike density, you can control its amplitudes and its location and so on, right? So this is how our brain is computing. And so in the industry, people also try to build chips, a neuromorphic computing chip, try to emulate this process. Now, what is the problem here? The problem here is that the state of the art for neuromorphic computing still fall far behind our brain. If you look at the left-hand side figure, there's some numbers here. So the current neuromorphic computing chips, state of the art one is comprises 10 to the power 10 transistors, but our brain has a 10 to the power 15 synapses, and each operation is more efficient. So each operation for a chip is 10 to the power minus 12 joule, and for our brain is 10 to the power of minus 15 joule per operations. So much more efficient. It's not just that. And then if you use transistor, if you saw the Intel low-high chip here, you need to use a 16,000 transistor just to emulate one neuron. Just to emulate one neurons, and so you can see that the power of even the state of the art chips is far behind our brain. And then we have a problem. If you want to make a chip more and more powerful, basically you rely on the scaling of the semiconductor devices, right? But the scaling of the devices is seeing our ceiling. Right now, we are foreseeing that TSMC will commercialize in 2024 2 nanometer transistors. But the physical limit of the silicon unit cell is 0.54 nanometer. You see, we are approaching there. So we cannot rely on the Moore's law and try to make the transistor denser and denser. So people looking in another direction, which is the computing architecture. Computing architecture has a lot of space to be improved. Especially there's something called von Neumann bottleneck. Von Neumann bottleneck is due to the separation of processor and memories. And the data shuttling between the two components typically consumes 90% of the energy, also 90% of the latency. So therefore, people try to look in this direction and try to invent something to overcome the von Neumann bottleneck. This leads to an area called in-memory computing. Basically, you put the memory on the processor together in a single unit. How can we do that? The basic element here is called memristor. Is a memory plus resistor is created this word. Basically, is a resistor has a memory. You can change the resistance so to store a single value in each element. Now, a typical memristor comprises 3 layers. Dielectric layer, insulating or oxide layer, and another dielectric area. So if you apply different voltages across the memristor, you can change the conductive filaments and change the resistors. And this is non-volatile. Most powerful use of the memristor is to arrange them, as you see on the right-hand side, is to arrange them as a crossbar array. Now, this crossbar array, basically, you can store by programming the memristors, you can try to store a matrix inside the crossbar array. So you can input a voltages, which is the vector input V here. Then the V, when the voltage and the current pass through the crossbar array, automatically you can do a matrix times vector multiplication instantaneously based on the circuit's basic law, Ohm's law and Kirchhoff's law. So this is one-shot computation of the matrix vector multiplication. This makes it extremely fast and extremely powerful because a lot of AI algorithms built on the matrix vector multiplications. So what we did in recent work is that we try to use this technology to empower the baseband processing of 6G communications. Why? Because in our communication, a lot of operations are also relying on matrix vector multiplications. For example, so we start with fabricating memristor. This is a kind of a memristor called resistive random access memories. If you look at this, the black photo here, this is a material stack for the memristor we fabricated. It combines titanium oxides, and hafnium oxide, and platinums. And so, and this we show that it can work. And actually, we make it into a chip. So this is 32 times 32 memristor crossbar arrays. And there are some characteristics here. I'm not going to go through the details. I just want you to look at the bottom right curve. You can see that if you apply positive voltage, the conductance will be increasing. If you apply negative voltage, the conductance will be decreasing. But there's some noise here. This is analog, so it has some noise. So, but you can overcome this noise by using reprogramming. For example, we program 10 times and pick the one most accurate. Okay. So its advantage is very, very fast. For the benefit of time, I guess I will not go into too much detail. Basically, what we did is that we implement OFDM, discrete Fourier transform, and also MIMO detector, and also a MIMO channel estimator. All of them involve matrix multiplication. So what's new in the DFT? So basically, the memristor array can only support positive real numbers, but so we use a multiple module connect together to implement a differential memristor crossbar array to implement complex and also negative, positive numbers. And so the advantage of this is one-step computations, while the traditional fast Fourier transform required a complexity of O n log n. So this is much faster. And what is amazing here is that actually memristor crossbar array can also implement matrix inversion. This is a circuit recently reported for matrix inversion. Basically, you connect the two memristor crossbar array storing matrix A together, use op-amp together. The result is that you can realize a pseudo inverse of the matrix A, as you saw on the equation below there. So what we did is that we built this one into a channel matrix inversion circuit for supporting MIMO detection. This is a supporting complex numbers operation. What is interesting here is there's a figure that we implanted a sequence of a transistor. By turning on and off this transistor, we can switch between zero forcing and MMSC MIMO detector. And this is our invention here. All right. And lastly, I just want to show you that we compare with state-of-the-art digital processor like Qualcomm Snapdragon, and also those are reported in the literature. Domain adaptive processor, combined FFT and MIMO, reported in the references. The general conclusion is this: latency, we can reduce it by more than 100 times, and energy we can also reduce by 100 times, more than 100 times. So this is a very dramatic performance improvement here, and the future looks good. We propose RN and power baseband looks good. This is some of the result reported in the literature. IBM researcher reported in the Nature that the per operation for memristor can reduce to femtojoule, and femtojoule is our brand energy consumption per operation. So this is approaching a brand level. And then the researchers are reporting the stackability of the memristor array. You can stack 8 layers of memristors over each other. Scalability is really small. We are able also to fabricate 2 nanometer by 2 nanometer memristors. So that's scalabilities. So we feel that this technology, not just this technology, or the analog communication technology also very fast. We discuss aircom, and unreliable connectivity. If you're able to combine the analog communication, analog computing together, we are going to able to solve the problem, 6G problem of 0.1 millisecond air latency problems. And so we feel that analog communication and analog computing is not dead yet. In fact, it could be a promising solution for 6G technologies, right? So lastly, I just want to conclude with this slides here. Martin Cooper is back. Analog communication is back. Analog computing is back in the area of the edge intelligence. 6G welcomes you back. So that's wraps up my talk. And thank you very much, and hope I'm in terms. Yeah, thank you.
Thank you very much, Kaibin, for this very inspired talk.
Thank you.
So now we are going to open to be open for questions and interaction with the participants. So if you have any question, please feel free to write your question in the chat box. Okay, so while we wait, people write some questions. I have one question regarding the latency. So how to deal with mobility in edge learning? I mean, if you have a mobility, the connection between the participating devices and the edge service, it's transient, right? Intermittent due to this mobility.
Yeah,
So how to get into a low latency learning process?
That's you mentioned that how do you finish learning process with mobility, right? And so that's a very good questions. Typically, when we measure the learning latency in the context of wireless communication, we don't measure by number of rounds, but it should be the total latency in terms of seconds. So basically, it's the number of rounds and then multiplied by latency per round, right? That's why we look at over-the-air computing process. This over-the-air computing allowing everybody to upload the model simultaneously. So basically, if you don't do that, the per round latency will be increasing with the number of devices. So therefore, if you can use this kind of simultaneous access scheme, you can reduce the communication latency per round to be very short. Now, as to number of rounds, computer scientists are working on that. They're working on learning algorithm to reduce the number of rounds. Wireless engineer reduce the latency per round, which is the absolute communication latency in terms of seconds. And so that is the one answers to your questions.
Okay, I have another question is regarding the collaboration between cloud learning and edge learning. I think they can complement each other, right?
Yeah.
So how to design an efficient cooperation?
Yeah, so that's absolutely right. While I'm focusing on edge learning, but there's a possibility to have a hierarchical cooperation throughout the networks. After all, the computation resources at the edge are somehow limited, and a huge model like GPT-3, which is a natural language processing model, it cannot be operated at the edge. It must be operated at the cloud. So I would say that more highly complicated, latency less sensitive, heavy-duty jobs should be delegated to the cloud, while those are requiring low latency and fast response time will be delegated to the edge servers. And of course, they can also try to cooperate if they can accommodate different time scales together. So they can also accommodate each other. And for example, federated learning people are also trying to build a hierarchical federated learning with a frequent updates at the edge and a less frequent update with the cloud. And so that's what you say is absolutely right.
Yes. Okay. Any questions? Oh, it seems you don't have more questions.
Great.
Yeah. Maybe we are running out of time and we need to conclude the seminar at 1 p.m. because we have another one.
Yes.
So I'd like to thank you once again, Kaibin, for your time and for this excellent talk.
Thank you, guys. Thank you, Daniel, and hope everybody will enjoy the World Cup seasons. And
yes.
All the best.
Thank you. Hope to see you soon.
Hope to see you in person. Bye-bye.
Yes.